Good evening and welcome to the IS&T Speaker Series. I'm going to pass it over to Bruce Pillen, our president, to introduce our speaker.
Tonight we have Dr. John McCarten, who currently works at L3 Harris, and I'll let him finish his own introduction. Thank you.
All right.
But before we even get to John, I also want to mention our next meeting is on February the 12th. We'll have Flip Phillips speaking about animation and movie technology, I believe.
Well, thank you, Bruce. I appreciate this opportunity because it allows me to do two things that I'd like to talk about, which is image sensors, because I've been working on these for 20, 25 years now. And I also want to talk about artificial intelligence a little bit and programming and trying to recognize images. So I'm going to try to combine the two. Okay. Yeah, let's go ahead and get started. And just a couple comments. I've been told that I speak sometimes like a fire hose. I just do a data dump on things. So I want to treat this kind of like we're all sitting at a bar and we're having a conversation. I should have brought beer, but I don't think they let you bring beer into the library. Okay, so that's that. And so let's just treat this as a lunch conversation. All right. The truth is a paradox. Why am I even bringing this up? It's an existential question. And one thing that I like to talk about here, just to get started, is this is from the Tao, the Book of the Way. The Tao has a very, very different perspective than most other religions. And the main reason is it was written right after the Three Kingdoms War. And most people don't realize this, but in the Three Kingdoms War over in China, like somewhere between 20 to 40 million people died. And this is in the year 300 AD. So it's a long time ago. And so it's a very different perspective. And it's sort of like our ancestors survived, we will too. It has a very different philosophy. And it's just an interesting way to look at things. So I want to start off because you were asking, who am I? So this is an existential question. And I was like, well, who am I? At least in terms of this group. Well, I'm a solid state physicist, right? And I did get my PhD studying low dimensional materials, and I worked a little bit with John Bardeen. If you don't know, he invented the transistor, and he also got the Nobel Prize for superconductivity. He's the only person that got the Nobel Prize twice in physics for that reason. And I have the claim to fame that his last paper, I think it's his last paper, starts with my name, because we had worked on some things, and he actually redid a calculation I did, which is kind of nice to actually say. Or you can say that I'm a nerd, one way or the other. And looking back in the 1990s,
Did he fix it?
Pardon?
Did he fix your calculation?
Yes, he fixed my calculation. Yes. Back in the 1990s, I also studied learned behavior and the pulse duration memory effect, and we looked at flows in metastable phase space. And this is back when I was definitely a nerd, because I was looking at this. But one thing I realized is, I'm not going to talk about this, but I learned that Mother Nature learned faster than the models that we had. Because when I was looking at this, I was studying something called phase organization. And this is like, I'm going to give you $1 billion idea right now, because a lot of people are looking at AI. And dislocations learn faster than elastic systems. And that's why they relax the strains that are in the system. So that's something that I learned. I'll get to that in a little bit when we start talking about AI. All right, made those comments. So nature doesn't hurry, yet everything is accomplished. On the going back to existential, well, existential questions or statements are good when you're talking about things, but your boss doesn't want to hear it, because tell that to your boss when the project is behind schedule. So the things that I did from 2001 to 2020 is we developed the Interline KEI Interline series. And I went back, we generated about 500 million in revenue. And Joe, you were part of that too when it came in. And that imager at the top was the 35 millimeters, the KI 2950. We sold about 250 million of those. And they went mainly to ViewWorks and Imperks. One's a South Korean company and the other is in Florida. And most of the screens that you looked at, I don't think the latest ones probably, but they were built with cameras that monitored just looking for displays coming down the assembly line with the defects in them. There's a lot of money in that, because if you think about it, how many displays are there on the planet? So that's where that came from. And when in doubt, always reduce the well dose. And then from 2006 to 2009, Joe was actually there with me. I forgot about this. We did CMOS image sensors and wafer stacking, and we were at TSMC and running around North Carolina. I'm actually going back to the fab in North Carolina next week, by the way, and in France, and we were doing some other things. And that whole effort actually died with the financial crisis, just for perspective. And there were about 250 CMOS engineers were just gone that we were working with. World moved on. The one thing that came out of that, and you're going to see this patent pop up 3 times during this presentation, is we had the patent on deep trench and full trench isolation. And you're on that patent.
I'm glad to see it alive and well.
Yeah, and it showed up on that. And it's basically to improve MTF. Is why you put the full trench in there, because the electrons can't diffuse. Right? You go to smaller pixels, that's where they did it. And then from 2010 to 2014, we went back to CCDs and did private equity. Actually, private equity bought us in 2012, to be honest. One interesting thing that happened is in 2012, on March 31st, Kodak sold all our CMOS patents, including this one, and they told us on April Fool's Day. And then private equity sold us to onsemi. Private equity is the only one that knows how to make money, because they bought us for $35 million. The year they had us, our revenue jumped to $100 million, and we were making margins of about 60%. But we worked for CMOS and onsemi from 2014 and 2020. Went back, we were working with fabs at TSMC in Japan, also in Israel, and Avanzano in Italy. We were making imagers, so I was back into doing CMOS again. And the lab actually got huge that we were doing the characterization in. Interesting story is the Avanzano fab in Italy, they being onsemi, didn't want to buy it. It's an old Micron fab because they didn't want to take over the Italian pensions that they were liable for. So that fab in 2018, 2019 timeframe was actually sold to the Chinese. And what was interesting, I went and looked this up for reasons I'll get into in a second, but the Chinese, I went and looked at SMIC, because Semiconductor Manufacturing Incorporated. One of the people on the board of directors worked for OmniVision, which was our direct rival. And starting around 2019, they immediately started slowing down the fab, because it took me 11 months to get wafers out at one point. And I remember screaming at my boss. I told her, get Tanner on the plane to fly over to Italy to get the runs moving again, because we were literally screaming at each other. And it turns out there's a company called G-Pixel that came out with some imagers around 2022 with a 3.2 micron pixel. And that's exactly what we had developed there. One thing I did do when I was going through this, I found my pandemic pictures. Doug Carpenter, when the place shut down, actually was collecting all the imagers that we had done, and he was taking them to the George Eastman house. So these are a lot of the imagers. Somewhere in here is the first megapixel imager ever made. So if you're doing development and characterization, you want to make sure you have someone in the fab that's your friend, because you got to go talk to them. Okay. Oh, and the one thing I do want to bring up, because I'm going to bring this up as a theme, because I know a lot of you here are image scientists. Steve Jobs always says the best programmer is no hardware. So there's a connection between people who do hardware and people who do software, and you got to be able to know that. And I'm going to start talking about computational pixels if I get to it. So my overview is I want to go through the greatest accomplishments in physics for the 20th century, and it'll make sense in perspective. Then I'm going to talk about still cameras just from 1900 to 2000, and the motion cameras from 1900 to 2000, and then trends since 2000, which are, we've gone to smaller pixels, more transistors in the pixels, high dynamic range, event sensors. I want to talk about black silicon, SWaP, which is size, weight, and power, automotive, and computational pixels. There is also analog per A to D per pixel, but I don't want to get into that. So those are going on. And then I'm going to completely shift gears, and I want to go to the origin of humor. And you go, and this is what I did during the pandemic, and it was part therapy, actually. Started writing a book, and you're going, why? And that's because there's a guy named I.M. Suslov. He was a Russian, I don't even, mathematician or something, and he basically was looking at AI. And he was saying that the reason humans laugh at stuff or have humor is because it's a way for us to correct bad input. And if you think about AI systems right now, and they're programming them, and they're grabbing everything off the internet they can get a hold of, how much of it you think's bad input? And so you have to figure out how to correct for that, right? And so that's why I started looking at humor and trying to study it. And what I want to do is I want to talk about hallucinations, and then I want to revisit the Turing test. I don't know how much any of you know about that. And then I'm going to do a tear down of the brain. And I want to work through the voice box first because I want to get to the visual path. But I understand what's going on with language more because the data is there. And then at that point, I want to introduce you to the Brain Dictionary. I don't know, how many of you, raise the hands, know what the Brain Dictionary is done at Berkeley? It was done in 2015. It's amazing because they mapped out the brain and how we think and what thought symbols are. And then I want to talk about emotions and training and words like murder and how baby laughter. And there's a difference between how men and women respond when babies laugh. Something amazing. And then I'll do a quick thing about the cerebral cortex and the cerebellum. And then I want to talk about Zipf's law, and it's how we organize data. And what's really interesting about that is we organize data for usefulness. And it turns out the statistics of how we organize words in our brain is the same as city populations. You know, there's New York City and then Chicago and then, LA, Chicago, Atlanta, et cetera. They all fall on a power law. And it's telling us how we do hierarchical energy, how we structure hierarchy. And it's the same thing with lakes and rivers. Lakes also fall on a power law. And if you think about it, lakes are connected by rivers. And it turns out it's a fractal geometry. Cities are connected by roads. Turns out it's the same fractal geometry. And the words in our brains and the way neurons are connected, it's the same fractal geometry, I believe. It's hard to prove. You know, you can't go in there and prove it, but you can look at lakes and rivers and you can look at roads and cities. It tells us. And it's very different than entropy and maximum entropy. Everyone talks about entropy and stuff, and it makes no sense to me. And then I want to talk a little bit about mirror neurons and von Economo neurons, and then the multiple vision pathways to the brain, in our brain. And I was surprised. I put that together this weekend. I went over my notes. My notes were a lot longer than I thought they were. So I don't think I can cover everything. And then I want to make my camera predictions for the year 2099. That's where I want to go. I don't think I can get through everything. So just stop me when we get to about an hour, and you can either invite me back or you can't. You don't have to. So if you guys, that's the way it is. So feel free.
Tell you right now, this list is not gonna be that stacked.
Okay. All right. That's, I knew you would say that. Okay, and it brings up even a question, what does perception even mean? Because this gets back to existential question. What are you even trying to accomplish? You know, even when you educate a child to educating AI, what are we even trying to accomplish? It brings up these existential questions. All right, so there's a quote from Bill Gates. I see little potential for the internet for at least 10 years. And he said that in 1994. So back at the turn of the century, people were making all kinds of predictions, and they're putting all kinds of lists together to rank things, and at the turn of the century and such. And I went to a talk for David Merman at the American Physical Society conference, and it was a great talk. And hopefully this gets along those lines. And there, okay. Here we are here in 1999. Looking back, what was the greatest accomplishments of the 20th century in physics? Quantum mechanics, special relativity, general relativity. Bah humbug, is what he said. He went, incremental improvements matter just as much as great leaps forward. Imagine if we gave someone in the year 1899 a laptop from 1999 and asked them, what do you think of this invention? And that's what the Apple iBook looked like in 1999, by the way. And he said, in 1899, individuals wouldn't be impressed with the Windows operating system. 1899, what does software even mean? Remember, that was the big thing in 1999 was the operating system. But they would be fascinated by just materials and packaging, the plastics, the keyboard, the integrated monitor, the wiring, the hard drive, the internal electronics. So where will we be in the year 2099? We're 25% of the way there now. And it brings up some questions, right? So predictions are difficult, especially about the future. That's Neil Bohr. So let's go back and make predictions about the past. And if you go back and you look, that was the Kodak film camera in 1899. You push the button, we do the rest. And basically, it was the ease of use that matters, the operating system. You buy it, you take the pictures, you mailed it to Rochester, they developed the film and sent you the pictures back. That's how we were 125 years ago. I couldn't find a Kodak camera on the internet from 1999, so I had to go to 1996, but that's where we were. CCD, the resolution was 493 by 373, and there was 1 megabyte of hard drive interim. That's what they had. And then if you go look at motion picture cameras, and actually I got a quote here, this is creativity comes from looking from unexpected and stepping outside your own experience. Masaru Ibuka, he was the founder of Sony. Right? And this is where we were in 1899. And this is where we were in 1999. I went and looked, that was the popular video camera. And you can see the form, fit, and function was a lot smaller. You could view the screen, it could play audio, you could play it back. And this is the craziest thing. I wanted to find out the resolution. It was 720p. And when I found that out, you can still buy this thing on Amazon. That totally threw me for a loop when I was looking at this. All right, so I'm trying to conquer the future. That's Mr. Beast. So the trends since 2000, I want to talk about smaller pixels, more transistors per pixel, which gets in the wafer stacking. HDR, global shutter, event sensors, which is even more transistors, and then black silicon and texturing. I'm curious, how many of you are familiar with black silicon? Joe is. Okay, nobody. Most of your cell phones have black silicon, by the way.
Borosilicon, black silicon, where it's etched to these fires.
Yes, I'll get to that. Swap, size, weight, and power. Obviously, everybody wants to go down that path. And everything's becoming a scientific imager. And then SPAD, single photon avalanche diodes. And then computational pixels. And I just want to mention something about Moore's law is the number of transistors on a microchip roughly doubles every 2 years. And cost is roughly halved over the same time frame. His original paper, he actually said the cost was halved. He didn't say that the number of transistors doubled. But if you assume that, you can work it out for the same amount of money in 1961 or wherever he made that. I think it's by the year in 350 years, every atom on the planet Earth would have to be a transistor for that much money. And then in 500 years, every atom in the universe would have to be a transistor. So there's always has to be an upper limit to where these laws can go. So, okay. Pixel scaling and trends. This is off Tech Insights. I've done a lot of work with them in the past. The standard thing is pixels are always getting smaller. And as of 2 years ago, they were at 0.56 microns. I think they're down to 0.5 now. Samsung has something. And just for perspective, the human eye, if you look at the rods and cones, they're about a 2 micron pixel pitch. And an eagle eye is on the order of about 1. This is what I've read. I have not done the measurements myself. Right. Pixels I have. So I get to that. Now, the things that are enabling smaller pixel pitches, I actually just grabbed this off the internet. First off, you can see the pattern that we had right here, because these are the pixels, the micro lenses, the light's coming in. But the light comes in, gets focused into the silicon, it's read out through here, there's a wafer bond, and now the electronics on the second wafer. The wafer stacking allows us to get things smaller. On this one, I'm not sure if the signal actually comes down this way or not, if it's just coming down at the array, on the edges of the array. I'll show you some in a minute where it's actually going through the pixel. But you can see it's starting to look more like neurons in the brain because we got more things going on. Another thing that allows you to make pixels smaller these days is they're actually typically transistors for older technology. The gates are on the surface of silicon. But now they're actually starting to bury them into the silicon. This is like a FinFET, except they're doing it this way. It's just to make things smaller because you don't have much space. So head in those directions. And just so you're aware, You know, people are doing wafer to wafer stacking these days. So basically, you know, these are 8 layers of silicon. So you can see that there's actually copper contacts coming through here. And what allows you to do this is this EVG Gemini tool. They can actually align to half a micron and do wafer to wafer stacking. And this gets into Moore's law, is that now we're having a harder time making things smaller. Well, we go in the third dimension. And they're stacking things like 12, 13 silicon deep these days, especially with AI. The problem with AI, this is a separate thing that I'm aware of. These AI chips, they actually get really, really hot. And they're actually making micro pores through these things and running fluids through them just to get the heat out. But the one thing that I want to point out is if you think about this, the stacking enables as much value as the entire Jefferson Road assembly area. This is down on Jefferson Road. This is where they make police radios and fire department radios. And all those people are basically doing assembly. And if you think about it, you can stack this stuff up and you can just package it. I've learned over my years that all the money's in the packaging. And if you think about it, like when you make a radio, there's a lot of parts in there and the bill of materials is pretty large. You have a lot of parts you have to get. And when you can start stacking things like this, all of a sudden your bill of materials goes down to 1. So there's a lot of cost savings associated, not just with the actual assembly, you make it smaller, but you don't need as many people to keep track of things when you go that route. All right, carrots may improve your vision, but alcohol doubles it. All right. More transistors per pixel. Okay, there's CCDs, and starting in the 1990s, we started developing CMOS pixels. There's a famous paper, Eric Fossum. He came up with this paper in 1993, CCDs of dinosaurs, and this was the pixel he had in that paper. It was 8T, and basically what you were doing is you were making a one-phase CCD that you would read out, okay? Now, I went back and realized people don't do an 8T pixel. They did 3T and they did 4T. So it took me a while to find this. This is the standard 3D pixel 3T pixel that most people used. And this is a source follower output. This was actually patented by Peter Noble in 1968. I had to go back and look this up. So he patented in 1968, but we weren't really able to manufacture it for another 30 years. Okay, so they knew what they were doing. It wasn't like, but you just had to wait until the technology caught up with it. And then this is the 4T pixel that people really started moving to because it allows you to lower dark current. And just so you're aware, I don't want to go into it, but there's something called a pinning implant that goes over the surface, and you need a transfer gate to make it work. But this shuts off the dark current, and it lowers the dark current about 3 orders of magnitude. Now, the interesting thing is that SWIR imagers, short wavelength infrared, mid wavelength infrared, and long wavelength infrared, mainly are made with MERCAD or some other materials. They are, most of them, 3T. Now, I don't want to get into all the details and capacitive transimpedance amplifiers and all that in the readout circuits, but they're mainly 3T and their dark current's higher. The Viz and the near IR parts are made with silicon, and most of them are 4T. And they have like a 3 orders of magnitude lower dark current because of that. Starting around 2000, all of a sudden, all the imagers became CMOS. Okay? CCDs actually stayed about flat. And as I was saying, Teledyne said their CCD sales went up last year. So, you know, this line, CCDs didn't go to 0, it's been flat. And they do have some benefits. I don't want to get into all that. But the interesting thing I found is in 2009, Sony only had 4% of the CMOS market. But by the year 2020, Sony had 40%. And the main reason is they got in the iPhone. By the way, that's a big thing. And they have actually, I was talking to Christian, they lost that contract about 6 months ago. And they had to lay a lot of people off. So Apple has a lot of sway. So moving on, there's now 5T pixels. And these give you HDR. There's all kinds of flavors. And there's even, you can get to more. But basically, if this photodiode overfills, and it goes over the transfer gate and goes onto this capacitor, and then you have to do 2 readouts. There's something called origin mode timing to read these things out. But just for demonstration, notice that this is an old method. The integration time is changing. And can you see the change there? It's not smooth as it went through. On the new one, when you have the HDR, you go through the tunnel, it comes out and looks smooth because you have so much more dynamic range. And image quality matters. An enterprise's most vital assets lie in its design and other created capabilities. That's Lee Kun-hee, founder of Samsung. And even more transistors in the pixel. Okay, and that's because we now have stacking. So over here in the top left, that's the first wafer. And then down here is the circuitry to read it out. This allows for global shutter readout. And just so you know, this is the silicon here. Does that look familiar to a patent that I was showing earlier? And you can see the full trench isolation. These capacitors here are really high density. They were developed for the DRAM market. And what's interesting is that layer of capacitors right there costs more than the rest of the entire wafer if you want to do it. But you have to get to the high density if you want to get the read noise down. You can do the analysis, the read noise scales as 1 over the capacitance. So you want the big capacitor. The downside about running with big capacitors is you actually have to consume more power, because when you transfer the signal from the voltage domain to the floating diffusion on those capacitors and then read them out, the larger the capacitor is, you got to put more current through there. And literally on your designs, if you do everything at once, the current rush in is on the order of amps, and it will fry your metal lines. So you actually, even global shutter, you actually stagger the rows when you read them out, but on the order of like a tenth of a millisecond or so. Otherwise, you're going to fry your part. And the circuit wafer is not shown. But this was in the year 2000, and the dBi pitch on this is about 2 microns. So they were doing wafer-to-wafer bonding with 2 micron pitch at that point in time. Okay, even more transistors. Event sensors. How many of you are familiar with event sensors at all? You know a little bit? A company named Prophecy, they've been working with Sony, and Samsung's been doing these too. The advantage of an event sensor is you basically are only taking the part of the scene that changes. And then you look at that. It allows you to look at things effectively at 100,000 frames per second, or up in that range. And that's great for things like missile tracking, as you can imagine. And the company called Prophecy, they were working with Sony. Now, one thing that's interesting is up on the image sensor blog, this past summer, there was a American Air Force colonel who went back to school in ETH over in Zurich, so in Switzerland. And he did his master's thesis on event sensors. And he was basically showing that you need to change the threshold depending on light level to get the noise down. That was his work. But in there, they had taken some event sensors and some other cameras, and they went down to Italy, went to a beautiful place right on the Mediterranean, and they took these telescopes and they pointed them up both during the day and in the evening, and they were showing that they were able to see the satellites flying over. And the event sensors were actually able to detect 3-4 times more satellites than the regular camera. I would love to actually go look at that and compare it to other cameras. But I was like, I want to go do a research project like that. You know, hang out on the coast end in the Mediterranean. That was nice. Okay, can you make cheese swim? No, but you can make butters fly. Make butter fly. So I want to shift gears just a little bit and talk about texturing that enables texturing. If you look at like a butterfly wing, a glass butterfly, their texturing looks like this. And just so you're aware, if you have texturing like that, it's a perfect AR coat, because the index of refraction changes gradually. If you look at like a standard lens that has an AR coat on it, it looks a little bit purple. And that's because they put layers on it and they tune it for the green. So you reflect a little bit of the blue and reflect a little bit of the red, and therefore it looks purple. This wouldn't look like that. It would look perfectly transparent or perfectly black, depending on which situation you're in. And somewhere around 2010, the people in the solar cell industry figured out, oh, if we take silicon and hit it with a reactive ion etch, and we get this, and it's a perfectly black. Okay, and this is how solar cells are made now. And in fact, when we were down at the home show around 2022, I noticed that the solar cells they were selling shingles, they all look like this. Because in the past, they'd have to take the solar cell and you were supposed to tilt it towards the sun if you wanted to optimize the collection. You don't have to do it with this because it looks great. And here's some data from a group out of Helsinki. And this is the reflectance of this black. And you can see it's almost zero at all angles. Even at 70 degrees, it's almost zero. And why do you need that? Well, you need that to go to low F number optics, because low F number optics, the light's coming in at all angles, right? And if you want to make a cell phone, the whole thing about a cell phone camera is you want to reduce the stack. You can only do that if you got a low F number optic system. And so there was a lot of work done in 2010 to 2020 period with black silicon to move things down. It says, journalism is simplify then exaggerate. Okay, and I have it for a reason. If you go to TSMC, this is the offering that they sell you. You know, this is how you get textured silicon. They will sell it to you for so much a wafer. But if you actually go to OmniVision and you do a teardown of their pixel, that's what they actually have. So OmniVision has actually figured out a better way to do black silicon, and it's that. And it's this, and you can see they actually have the deep trench isolation in here. And if you actually do a little bit more of a teardown and look at the passivation, the interesting thing is they moved to Al2O3 instead of silicon dioxide. And the reason you do that is Al2O3, the oxide density is about 30% higher. And therefore, you're 30% more likely to actually make sure that your silicon is terminated properly with an oxide. I figured that one out. And, you know, these are things that you don't think about, but people who are doing the solar cells actually had worked out all this stuff. So they've gone to aluminum passivation, and that's migrated into image sensors. Okay. Some people do hafnium oxide for the passivation too. Sony does. So there's other passivations, and the whole reason you do this is to get the QE up in the IR. 940 is kind of a magic wavelength, because if you're driving your car and you look at the sun, 940 gets absorbed by the water in the atmosphere. Therefore, you don't get blinded. So your automotive system, your self-driving car, think about it. If you wake up in the morning and you start driving right into the sun, the camera is just going to get blasted. That's why they want to do things at 940. They want to get that up. And the other thing I'd mention is the reason this works on the black silicon too is when it comes in, you can think of it scattering like this, so it increases the light path, so it's more likely to get absorbed by the silicon. What's really going on, though, is when the light comes in, it really slows down the speed of light by about a factor of 3. There's a beautiful paper by the guys at the University of Minnesota showing this, and it's because you modified the modes in the system. All right. Steve Jobs said, great things in business are never done by one person. They're done by a team of people, obviously. And obviously, that's the whole reason you've gone to swap and lower F number optics moving forward. All right. And just so everybody is aware, this tool here is an EVG Hercules nano imprint lithography tool. And you can make these wafers of lenses. And this is how you do wafer stacking. So you'll make your silicon wafer and you stack up lenses on there, and that's how you make the modules. Almost all that stuff's done over in Malaysia, by the way. So, you know, you can crank out like 10,000 cameras off of one wafer. And that's why they can keep the price down. If you look at it. And going back here, I mean, you can buy this 3-camera module on eBay that fits in a Galaxy camera for 20 bucks. You know, that's what the prices are now. Okay, and like I said, comment on packaging and money. The one thing I've learned in this business is all the money is in the packaging moving forward. Okay, so Einstein said if I had 1 hour to work on a problem, I'd spend 55 minutes on the problem and 5 minutes on the solution. So what is the problem? Well, for the scientific imager, you want to do a few things. You want to know exactly where the photon comes in, because you want to make a pretty picture, or you want to do a spatial measurement like ground sampling distance. You want to know when it came in case you want to do time of flight, or if you want to do blur correction. You want to know its wavelength, so you know its energy, or if you have things, you can figure out the chemical composition. You want to know what angle it came in for phase detect autofocus, and you would like to know its polarization for both chemical and also automotive and things. So, and the details they actually depend on the application. So Sony, Like this is what they do, phase detect autofocus. In a pixel like that, you're actually, there's 2 pixels under that micro lens, and you can tell which direction the light's coming in. Well, people, this is what cell phones are doing now. This is 2021. OmniVision has come up with, this is why they want to go to small pixels, like 0.5, is because you actually can group them in a group of 4 now, and you put a micro lens over the group of 4, and you can tell what direction the light's coming in. And from that, you can do really rapid autofocus. Okay. There's other reasons you want to do this, and this is actually important for some of the people in this room. Oh, sorry, I'll get to that in the next slide. And you can also do planoptic cameras. I don't know how familiar people are with planoptic. But you take these pictures, and basically if you took an image with just the pixel in this corner on all of them, and you step through, because this is a 25 by 25 pixel, you'd get this image. And then if you pick another pixel here and you take all of those and make an image, you get a different depth of focus. So you can build that up. And Lytro did the work in 2014. For aberration correction, there's a paper from 2022 where they're actually talking about doing satellites, making big satellites. And what they want to do is, you can see here, they basically have a 5 by 5 pixel, and you can detect which direction the light's coming in. And the whole reason for that is then you can correct for the aberration of the wavefront error, because they want to make their optics cheaper, so that you don't have to spend so much time getting everything perfect. And this is an example where they come in and say, okay, this is what the image sensor actually sees here. But if you do all these corrections, you end up with something right here. All right, you can see the lights and get rid of it. And if you think about it, if you have 2 segmented mirrors, and one of them is off of focus, so it's like shifted over 1 pixel, and the other one's off of focus and it's shifted over 1 pixel, you can figure that out. And you basically would have 2 images that were shifted, and you can then figure out what you actually have. I haven't gone through all the math, but it's pretty clear what's going on there if you think about it. I was looking about a year ago. It's like all the best patents right now in image sensors are coming out of China. Let's shift gears a little bit. If you think nobody cares if you're alive, try and miss in a few car payments. Okay? And I'm going to shift gears literally. Sony has been working on the roadmap for image sensors. All right? And it's been announced that the Sony Honda car is supposed to come out in 2026. I know Toyota is working on one also. And on that car, it's supposed to have 45 sensors. Now, not all of them are image sensors and cameras. They got radar and other things on there, but that's a lot of imagers. And it's interesting because Elon Musk, he said that you only need a visible imager for a self-driving car because that's all humans use. It's going to be interesting to see how this all plays out. I don't know what's going to happen. So there's currently a battle going on. It's like, okay, and there are 10 types of people, those that understand binary and those that don't. So people might have missed this, but this happened during the pandemic in May of 2020. Sony came out with the IMX500. And this is basically an imager that you can program to do pattern recognition. So you can do it to recognize faces, and also to put it in cars for, like, somebody walks out in front of it or something, it stops. So it's here, and they call this Edge AI. All right, I tried to get a hold of one of these sensors in the evaluation kit. They won't give it to someone like me. You have to be working for one of their big partners. But it's here now. I'm going to get to some other ones in a minute. Shifting gears just slightly. Single photon avalanche diode, even more transistors in the pixel, because you're basically doing time of flight. So you illuminate a scene with a laser, the pulse goes out, hits, reflects, comes back, and you can measure the time of flight. And then you can do a 3D mapping of the image. Okay, so there's lots of imagers out there that do this. I think the first was the Sony IMX459. So there's other ones out there. And just so you're aware, you can buy, this is a Canon MS500. It's has a SPAD sensor in it. It's claiming, there's one paper that claims the read noise is 0. But we have sub-electron read noise cameras now. So, I mean, they're basically doing photon counting at this point. And you can get this for $25,000. Actually, it's down to $20,000. I've looked. But this is really interesting, and this gets into computational pixels now. I was at a conference about 2 months ago, and the same guy that was doing the Canon camera is talking about what they're working on now. And they basically want to be able to do time of flight where you hit a light, send a light out, and it comes back. And if you think about it, if you're in a bright light situation, you got noise coming in because you got other photons. So what they want to do is only trigger this 5x5 pixel if 2 or more pixels trigger at the same time. That way you can see, you can do time of flight in bright light situations. I was like, this is brilliant. And that's what they're working on right now. So you can see how the world evolves, different problems need to be solved, and you have things. So this gets into computational pixels. And that's a good segue into what I was going to talk about next. So I'm going to show you this video from a company called Ubisoft. They were totally off of my radar until about 3 weeks ago. There were a bunch of MIT guys also working with the University of Wisconsin. And they're basically doing SPAD imagers. Okay? And I'm just going to play the video so you can see where the world is moving right now. And their imagers actually detected 1,000 frames per second. So you can see some of the quality differences.
At Ubisoft, we revolutionize how machines perceive the world by combining next-generation image sensors with advanced computer vision algorithms. This video highlights some of our passive perception capabilities. Here, we set up our system next to a low-light machine vision camera. Let's dim the lights and test how well they can perform when we really push their limits. As you can see, both systems are set up to highlight QR codes whenever they're detected. They both perform well when the motion is slow, but what if we speed things up? The low-light machine vision camera isn't seeing anything, but the Ubisoft solution is capturing every single one. To see what's going on, let's examine some data more closely. Here's a video from the low-light machine vision camera. It looks good here with slower motion. However, with faster motion, every frame has enough blur and noise to make the QR code unreadable. Let's see how the Ubisoft solution performs. To put it mildly, it's able to capture a lot more. Of course, processing all this data requires a lot of advanced technology, and that's what we offer at Ubisoft. In this next demo, let's see how the Ubisoft solution compares to the high-end automotive camera shown here. It looks great right now, but let's see what happens when we venture off these well-lit public roads. We can already see the lack of detail in the trees, especially on the edges of the frame which aren't covered by our headlights. What if we head in deeper and shut off our headlights entirely? We can recover a little detail by turning up the gain, but this only helps so much. Now, take a look at what the Ubisoft solution is able to see. The automotive camera can't even resolve the intersection to the right, but it's not a problem for the Ubisoft solution. And watch what happens now when the headlights come on. The image adapts instantaneously and preserves detail in the darkest and brightest regions of the scene. The Ubisoft solution is clearly better here for perception. But what about more common situations like driving through a city at night? Well, let's see another demo. At first glance, these clips may not seem too different, but let's look at some individual freeze frames. Here, the automotive camera blurs the sign beyond recognition, but the Ubisoft solution captures the sign, the bricks, and even the text on the lamppost with perfect clarity. In some frames, signs aren't even visible with the automotive camera. Just imagine if this had been an obstacle or pedestrian. The differences are even more stark when the two results are processed to reconstruct a 3D model of the scene. Here's
Okay, so that's pretty much it. You can go on and on, but it's just to show you an idea of what you can do with SPADs and computational pixels, and throwing more transistors in there along the way. So
These single detectors spread out really fast.
that's right. Yeah. It's interesting. Well, remember we've worked on TDI parts in the past. The Chinese are currently working on SPADs for doing TDI. And they're the only ones I'm aware of doing that right now. Okay, moving on. I collected a lot of data trying to disprove confirmation bias. The results were exactly what I expected. And just so people are aware, you can actually pre-order their evaluation kit if you want to look at it. I know that Ubisoft gave a presentation at the Consumer Electronics Show about 2 weeks ago, and it was well received. I was trying to find the video of their presentation, but I couldn't. I was looking it up online. It wasn't available. All right. Other comment. Mobileye, and there's other companies that are doing similar things for the automotive market. I know GM and Tesla are trying to do self-driving cars and the cameras internally, but Mobileye, it's like selling it to that's what is Stellantis or Nissan and other companies. It's going to be interesting to see how that all plays out. Is there going to be a separate company that does the self-driving cars, or is it going to be done internally at the big guys? I don't know the answer to it, but they're doing very similar things here.
Now to an example of what can happen when a driverless car meets road construction. This Waymo van got stuck at an intersection in Chandler after orange cones apparently confused the system.
I've seen people get confused by orange cones.
This is true.
Passenger Joel Johnson recorded the whole thing. Waymo says the car alerted a remote fleet response specialist who gave the car some incorrect guidance. A roadside assistance team got the car back up and running, but just a little ways down the road, yep, got confused again. A human driver had to come over and complete Johnson's trip.
Oh, it's a win for humans over computers and robots.
Yeah. This is a good place for me. I'm going to stop here in just a minute, but I want to shift gears a little bit because I want to start talking about programming and artificial intelligence, because now we're trying to take all these images in and extract useful information. And this is an example of a self-driving car that saw a traffic cone and freaked out. It didn't know what to do. And there's other examples like this one, which I don't have any sound on. But luckily, no one got hurt here. This is a Tesla, all right? And obviously, they had trained it to drive in the highways in California, and it's out in West Texas somewhere. I don't know what the heck it's thinking. Like, it went right through the stop sign, right through it, and, it crashed. So this is a stupid self-driving car. Now, I'm going to show you the next one. Somebody does die, all right? But it also indicates to you emotions are important when you're trying to look at this. So I'm just going to play it. It's about 20 seconds.
On the morning of May 5th, 2021, Stephen Hendrickson was driving his Tesla Model 3 to work. His car was in autopilot as he drove through Fontana, California. At about 2:30 a.m., an overturned semi-truck appeared in front of him. Moments later, he was killed.
When you're training something, certain events have more weight than others. Okay? And the way humans actually deal with that, it's their emotions. When it's something traumatic, those are the things that we remember, right? And it's not clear to me how that stuff's being handled right now and what you're trying to do moving forward. So this is probably a good place to stop. So let me just circle through here what I was going to do. I just make a couple comments. During the pandemic, we started writing a book on humor, part therapy and part invention. And as I said, in 1992, I.M. Suslov suggested that humor is necessary to correct bad inputs into our brain. And if you think about it, why do we find slapstick funny? Because it's a bad input, right? It's somebody's doing something that you won't expect, right? ChatGPT-5, which is supposed to come out, is currently behind schedule. The energy bill to program ChatGPT-5 to run for like 2 months to program it is around $500 million. That's ridiculous if you think about it. I mean, college is expensive, but it's not that expensive. You want to train somebody's mind to do something. And what's even more ridiculous is the U.S. energy consumption is predicted to double by the year 2035, all due to AI. I mean, that's even more ridiculous. So I want to talk. The rest of this, I don't have time to go through, but I wanted to talk. Yeah, for all the data centers, but the rest of this talk was, I wanted to go through because I had like 3 years during the pandemic, and I was working on this book, and I basically did a teardown of the human brain. Why don't we just stop now, since I've gone for an hour. I really appreciate having the opportunity to talk about this stuff. All right, and we'll go on. I couldn't tell if I was putting people to sleep or not. Does anyone have any questions, comments, or I should kick it over?
All right, thanks, John. Folks online, we're going to adjourn the presentation at this point. But we do have the opportunity for questions. John's given us a lot to think about. And does anybody online have questions, or anybody in the room?
Two questions. I see these things come by all the time. And so every time I do, I have to question it. A half micron pixel, what's it good for? The point being, where are you going to find a lens that can resolve to half a micron? And if you can't resolve it, what's the point of measuring it?
Well, that's the whole point of this. That's a 1 micron pixel. And what you're doing is you're able to figure out what the direction of the photon is coming into that pixel. And from there, you can extract that extra
But
information.
if your area disk is 2 microns big.
You can still detect which direction the photon's coming in. Therefore, there is extra information in there because you're mapping out the light field.
So diffraction doesn't impact that at all.
No.
Okay.
There's a 3 micron micro lens over the whole array of pixels. So
Well,
it's
this is actually
directing-
half micron pixels, 1 micron micro lens.
Okay, 1 micron micro lens, but that's what's directing the light. And so it's only being detected by certain pixels. And that's how you determine that. Or I assume that's how it works.
Yeah, the one thing I've done pixel modeling optics, micro optics in my life, and the one thing that's kind of surprising is you do get the airy disk type solution, but the first order you still get kind of ray trace. So even though it's kind of blurry and coming down, it still looks like it's still going in the same direction. It's
The area disk still has a peak in there.
exactly, it has a peak in there and you can trace it out. So yeah.
Okay.
And you can actually see the reflections and all that.
Second question, with the OBI thing, I've seen that demonstration over sensors over my entire career.
OB?
What's the name of the company? UBI.
UBISEP, right?
UBISEP.
High res with the high sensitivity.
Yeah. So why is that not photon shot noise limited? If your quantum efficiency is,
100%.
right, improved from 60%, right?
Yeah.
Say it's a lousy sensor only has 60% quantum efficiency. Now you go to 100%, but that difference that you showed there was more than a stop. It was huge.
Oh, the
And-
UBISEP one?
Yeah. And
Oh, I'm sure they probably grabbed a crappier camera just to make it look like theirs was better. But the nice thing about the UBISEP one though is that you could see that the motion blur was gone. That was the main thing to be looking at.
Which meant they integrated for less time, significantly less time.
Oh, that's a good point. Yeah. So at
Which
that
means they
point,
had significantly less photons.
yeah. So they had to be opening up the F's number. I mean, reducing the F number, right?
So is
You
it
still
snake
need the
oil?
photon at the end of the day.
Yeah, exactly. You need the photon at the end of the
That
day.
readout is great for a really low noise readout because 1 electron becomes 1,000. You detect that easily.
Yeah, well, there is one advantage of the UBISEP. It's the video, so I can't play it. But the thing is if you're driving like this, because they're capturing all the photons and time stamping them, they can actually do the averaging. As the thing moves, they can add that back in. So, and they're doing that. These are computational photons. So they're actually taking the photons on the left and the right, and they're averaging back in to pull out more signal. So it's, yeah.
Yeah, I wish, so if we get a chance to hear you again, I would love to hear this, their presentation was, look how good we are. And I'd love to hear, and here's how we do it, because otherwise it just feels like another snake oil.
Well,
I'm sorry, I'm skeptical about these things. I don't know about you guys,
yeah,
but
well,
technology has been announced that says we do this wonderful thing, but it's a black box and trust us, it does it.
but I'm not their sales rep.
I
So
understand.
I'm not going to play,
No, I'm not-
but
I'm not
I
saying
do know there's been a lot of work with SPADs and being able to timestamp stuff so you can actually rearrange the image as you're moving through and readjust for the motion blur. And there's some very sophisticated algorithms for doing that.
Sensor 2099. So everything there is to know about a photon, right? When it got there, what angle it came in at, and their claim to fame, I believe, is just having a big computer and big software behind it, being able to process all that information into a usable image. I mean, that feels like 2099 stuff, right? You know every bit of information about every photon your camera is seeing, you've got a big enough computer behind that to make some sense of it, right? And then you're using that information. And I would add to that, and something that I've really talked about, multispectral. You had said, at one point you had said that, Musk said all we need is visible. To me, that's the dumbest thing I've heard.
You want to be able to see through fog.
Perhaps the minimum, because we know that there's a good intent for having that. But multispectral is, when you think about now, an interesting question is what percentage of image sensors sold today is entirely, a human being never looks at the image, right? So entirely processed by a computer, right? And that number will just increase exponentially. So why should our sensors be limited by what a human eye can see? That just seems silly, right? And so, there's only a certain range of spectrum that's available, assuming you're navigating the planet Earth, right? As you mentioned, things get absorbed by water, things get absorbed by, the air. But there's a huge range of information there that, that self-driving car that hit the truck that was overturned, right? Well, I mean, radar is already a thing, LiDAR, all that stuff.
Yeah.
Why didn't that sensor see it, right? Why didn't, there's just a whole, or a thermal imager would be like, holy shit, there's a big thing in front of me versus, there's a few less photons in that spot.
Yeah,
right?
well,
Yeah.
Called the Surface Optics of California, and they are that is doing panoptic imaging, multispectral panoptic imaging.
Yep.
They're putting basically arrays of filters at the entrance pupil of the plane, and then imaging it onto. They're using a micro lens, covering a 4x4 array of pixels. So there's a super pixel there.
But when you say multispectral, what wavelengths is it dealing with?
So
We're talking about IRUV, or are we talking?
They've done it in the kind of UV to vis range, and then also in the SWIR and midwave. And I mean, I know a little bit about them because I worked for them for a year.
okay.
So that all that makes sense to me is the future, that a human being is not going to be looking at these images, right? And so it shouldn't be limited to what humans are used to looking at.
Yeah, that demo looked like it was dipping into the IR because the tree leaves were very bright compared to
That's true.
other things around it.
Yeah, actually, the camera they were probably comparing about probably had an IR filter on it, and theirs didn't. That's all it came down to.
Thank you, folks online here. I have a question here. Thank you for a very insightful presentation. Can we know your vision of how image sensors will look like in 2099? I'm very intrigued to know your opinion. Thank you again.
I guess I can go to the very end. Let's go to the conclusions. Focal plane arrays will effectively be scientific imagers stamping every photon. So it's what we were just talking about. More computations will occur at the pixel level. Pixels will look like a collection of neurons. That's where we're headed, because you can see all the wiring, and we're doing stuff, and we're going to start looking at things connected horizontally too. Just for noise, a swap, that size, weight, and power will continue to improve. Data compression and object recognition will blow us away. Because we're going to figure out how to just send the data to where things are changing. And then moving on, machine learning will evolve to organize data for utility. We're really not there right now. And I didn't talk about Zipf's law because we didn't get into it. But the way they're organizing data, right now it's just curve fitting. You take this data set and you throw it and you feed it $500 million of electricity, and you have 1 trillion fitting parameters and get an answer out. And that's going to change a little bit. I guess got to look at my own notes here. Machines will evolve to have something like emotions, to weight certain events as more important than others. All right, that's something that's coming in, and operating systems will be very easy to use. This is just kind of like, I have a lot of other comments going through there, but those are just the high level things. But I really think that there's something equivalent to emotions are going to come into play, because we got to sort out what's important and what's not. And that's why humans evolved emotions moving forward.
You think we'll have curved focal?
They exist now. Because they have issues.
Good curved focal.
How big do you want it to be? And how curved?
Like the eye.
I can point you to, there are, once about every 2 years. Yeah, once every 2 years, there's a paper, there's a note up on the image sensor blog. And I've seen people who have built them, you know, and they're curved and you can look at it. But I know nobody has moved forward with any of that stuff. You know, there might be cameras out there with them I'm not aware of. But I can point you to some of the papers if you want. Because I know if you go to the image sensor blog and just search curved focal planes, it'll pop up. Because I know it's like every 2 years, there's like one article about that.
I have one more question here
It
online.
would be tough to build.
Yeah,
I
know.
It would be easier to, I mean, ultimately, he had aberration correction, right? As one of the applications of the million things you presented. It basically just correct for it, right? You're not gonna, don't design your optics for it, but design your sensors so that you know what the aberrations are. It's very hard to make, because we're talking about like really big geometric.
It's not as hard as you think, because I remember the papers, because you can take silicon and you can curve it, and then you can take the BSI imagers and you thin them down and you can actually put it onto the curve. So people have done it. It's been done before, and they exist.
Yeah, that 8 stack, that's like, you know.
Yeah, those are a few microns.
Not even.
I mean, the silicon's like so they start off with something that's curved, and you can apply the silicon to. They've done it, all right, and they've had them work. I've seen it, but
And that can figure.
Yeah, but going into production, I don't know how easy it is.
Got another question for you here. Following this, would love to know your opinion on how does the technology of meta optics, e.g. meta lens, impact the design of image sensors in the future?
I'm not quite sure what they mean by meta lens. I do know what they mean by meta lens.
Yeah, METALENZ.
Yeah. I wish I had a picture. Does anyone here know what a meta lens is?
It's a structured surface.
That's right. Yeah, it's basically a planar lens, and what they do is they do MEMS. They etch it out so it has a higher density in the center and less density as you go out. Yes, yeah, that's how they work. I've heard that there's some of those have actually gone into cell phone cameras now, but I don't know. There's also grin optics where you have a plain piece of glass and you change the index of refraction as you go from the middle to the outside.
Well, I was wondering if your metal lens is effectively that.
Yeah, that's exactly what it is.
Punching up trenches in there, the effective refractive.
The problem with meta lenses, if I remember right, is they have very bad chromatic aberration. So they're only good at a couple wavelengths. I remember talks on this now. I'm having to go back in my brain here. I haven't worked with them. I haven't gone through any of the details, but yeah.
Very good, thank you. Any other questions online in the chat window? Volume up here. If not, John, thank you very much.
Rather than try pass it over to.
Oh, wow.
Yeah.
I'll have to hang it up when I get home.
We appreciate you coming to spend your time with us tonight, and thank you very much. And there's a little remembrance for your participation in this.
Okay.
Could be a part 2 coming. That's what I'm hearing.
Yeah.
That's what I hear. Yeah.